All right, I think we are live, and this is session 5 on continuity and differentiability. And here we have Tanmay with us, who will be joining us in between and will be pitching in as well. So good, great to have Tanmay here because he reminded me to carry on with this experiment and finish off the topics that we had planned to do. So before I see you on 2nd of July, we need to finish on continuity and differentiability. And of course mean value theorem as well. So let's see what we can bring in today, and then from there we will move on. So Tanvi can put his microphone on mute, and we'll start with our presentation. Thank you. We are going to be looking at the concept of continuity today. Of course, we are looking at an understanding of how we have okay, so this is not the presentation that I want. So I want to talk about, this is my second lesson. So we are looking at continuity of a function. So is that the right slides you are able to see? Tanmay, what do you think? Are you able to see the slides?
Yes, ma'am.
Are you able to see the slides now?
Yeah. No, ma'am, not right now.
Not right now? Okay, let me see. It's not minimized, I think. So, yeah, is that on?
No, ma'am, I can't see the slides.
Okay.
Yeah, I can see your face right now. I can't see the slides.
Now it's on.
Yes, ma'am.
Right. So this is what we had talked about last time, what we mean by continuous functions and continuous at a point. So the definition was, if f is a real function on a subset of the real numbers, then c is a point in the domain of f. Then we say that f is continuous at c if the limiting value of the function at c equals the actual attained value of the function at c, which again spells out to be same as saying that the left hand limit and the right hand limit at c must be equal, and not only that, they must be equal to the value of the function at c. So this is how one checks whether a function is continuous at a given point. From there, we are looking at also an extension of this little result, which results into very important useful theorems, which were if two functions f and g are continuous at a real number c, then there's some difference product and the quotient provided value of g at c is not 0 is also continuous at the point c. So this is one theorem which will come in handy as we go along. And another theorem that we mentioned was, if I take two functions f and g, then f composed with g, which is defined at c, is also continuous at c if g is continuous at c and f is continuous at g of c. So this is a very useful result, especially if I'm talking about composition of functions like sine of x squared. So if fx equal to x squared is continuous and sine x is continuous, then the composition of the two will also be continuous functions. So this is something that does help us as we go along. Another definition that we are interested in examining further is what we mean by function continuous. Not at a point, but a real function f is said to be continuous if it is continuous at every point in the domain of f. So this is a result that we will be examining and using further today. And at the same time, small results like these, let's think about how they stand true. Every polynomial function is continuous. Every rational function is continuous. In terms of the sine and cosine, they are continuous functions. So we had briefly talked about these little results last time as well. Every polynomial function can be thought of as sum of, starting with identity function, then product of x and x will give rise to x square or x cube if you take it 3 times. So the sum of continuous functions will be continuous, results in a little very important conclusion for us that every polynomial function is continuous. If you keep the graph in mind, that also helps us to understand why all polynomial functions are continuous. When we say every rational function is continuous, then again, going back to the definition, it's continuous in its domain. And therefore, don't worry about the points where there is a singularity. So if I take 1 by x minus 1, then the function is not going to be continuous at x is equal to 1. It's not in the domain. X equal to 1 is not in the domain of that function. So even if the graph breaks at x equal to 1, well, that's perfectly fine. In the remaining part where the function is defined, the function would be continuous. So we'll be referring to this result as well in some places as we start using the concept of continuity. Okay, now let's look at this problem which I have taken from your NCERT textbook. It says discuss the continuity of the function f defined by f of x is x plus 2 if x is less than or equal to 1, x minus 2 if x is greater than 1. So looking at this definition of the function, what do you think we are dealing with? What kind of a function are we getting into, and what does it mean by discuss continuity of this function? So Tanmay, if I may just bring you in, what would you think is special about this function? What kind of a reaction a student would have when you look at a function like this, and can you just examine it and comment whether it's going to be a continuous function or not going to be a continuous function? What do you think? So I'm going to just get out of these slides and focus on Tanmay so that he can also help us think about what we are looking at. Yes, Tanmay, what do you think?
Well, this is basically a piecewise function consisting two polynomial functions inside, if you want, that's what I should call it. So for x is less than 1, the function is basically x plus 2,
Right.
and um, for x is x greater than 1, the function is defined as x minus 2. So basically for all values of x other than 1, this function is a polynomial function, so it is continuous, because as you just said, all polynomial functions are continuous. However, at x is equal to 1, uh, clearly the left hand limit is 1, like if you substitute 1 for x, 1, it is 1 plus 2, which is 3, whereas the right hand limit is 1 minus 2, which is negative 1. So the two left hand and right hand limits here are not equal, and the value of the function is of this 1 plus 2, because for x is equal to 1, f of x clearly is x plus 2. So here the limit, which does not exist, in fact, is not equal to the value of the function, and as the function is continuous at all points except x is equal to 1.
Okay, that sounds quite good. If we look at this function, as Tanmay said, there are for x less than 1, it's a polynomial function. X greater than 1, it's a polynomial function. So if we don't consider the behavior of this function at 1, but we just generally say, well, f of x is a polynomial both ways, and therefore it's a continuous function, then there is something wrong in our observation. Because the result said that the function has to be continuous at every point of its domain. Then it's a continuous function. So here the idea is, and as Tanmay was trying to examine the behavior of the function at 1, again, something that we did talk about a lot in grade 11 was what kind of a graph will this function have. So if you think of it graphically as well, and if you try to plot it, you would see that at 1, there is something strange happening. So on as x less than 1, it's a straight line, x greater than 1, it's a straight line, but at x is equal to 1, it's not going towards the same height. So Tanmay, if you can put your microphone on mute. So we are looking at something happening at x is equal to 1. This is where the whole discussion therefore has to be focused on. But you can't ignore the domain which is on the lesser side of 1 and the part of the domain which is greater than 1. So when you are algebraically asked to discuss continuity of the function, then it is over the entire domain, not only at x is equal to 1, but at x equal to 1, we have to examine it going by the definition of continuous function at a point. So how do we put down this solution? Again, graphically, yes, we can be very confident and can claim that the function is not continuous as at x is equal to 1, but for all other values of x, it is continuous. Therefore, over the entire domain, the function is a non-continuous, or as it is, the word is discontinuous function. Algebraically, now this is again a solution straight out of your NCERT textbook. For x less than 1, I have to examine the behavior, and therefore we take any value, say c. If c is less than 1, then f of c is c plus 2. Limit of fx as x tends to c is limit of x plus 2 as x tends to c. And it's limit of a polynomial. Therefore, you are just substituting and you get c plus 2. So putting this two facts together, the function is continuous at all real numbers less than 1. So this is the way NCERT has talked about. At the same time, in another problem, they have taken the help of, which we will also do. We will take help of these results. Like Tanmay just now mentioned, for every x less than 1, fx is a polynomial function. And all polynomial functions are continuous. So you can get away just by writing that for x less than 1, f is a polynomial function, therefore it is continuous. Similarly, for case 2, when x is greater than 1, you may take a c, which is an arbitrary value, real number, but greater than 1, and examine what is happening to the limiting value and compare it with value of the function. If they are equal, well, then the function is continuous. So you can say, therefore, the function is continuous at all points x greater than 1. The same thing as in the case 1, you here use and say f is a polynomial function for x greater than 1, therefore f is continuous. Case 3 would be at c equal to 1. So we will then look at exactly at c or at x is equal to 1, what would be the behavior of the function? Is the left hand limit equal to right hand limit equal to the value of the function? So for that, you go back to the regular method of finding the left hand limit. So limit of fx as x tends to 1 negative. That's the notation that we use. Replace fx by the rule that function follows when x is less than 1. So you will have limit of x plus 2 as x tends to 1, which is nothing but 3. Right hand limit of f at x equal to 1, similar way. Limit of f of x as x tends to 1 from its greater side. So one positive sign is written there. And then that gets replaced by limit of f of x minus 2. Fx gets replaced by x minus 2 as x approaches 1 from its greater side. Same as 1 minus 2 and therefore minus 1. So the left hand limit and the right hand limit are not equal. So the function is not continuous at x is equal to 1. So the conclusion can be stated as x is equal to 1 is the only point of discontinuity of f. Because the question said discuss continuity of the function. So you can state it in different ways. You can say that the function is continuous over its entire domain other than at x is equal to 1. But the function is continuous for x less than 1, for x greater than 1, but discontinuous at x is equal to 1. So that's the way that one can establish the continuity of a function over its entire domain, right? So that's how we go. So let's look at another problem that we have and see if we are looking at some other way the same concept is talked about. So we are looking at our next problem now, where we are going to be talking about modulus function. Discuss the continuity of the function fx is equal to mod of x minus 4 by x minus 4, x is not equal to 4, and 0 when x is equal to 4. So it's a very regular function that you are quite accustomed to by now. And again, here the emphasis is that it does not ask you to discuss continuity at a point, continuity of the function. So again, very first step to be would be to rewrite the function so that you can understand it better. So again, going by, if x is greater than 4, then f of x is x minus 4 by x minus 4. I think all of you are pretty accustomed to doing this kind of a change. If you still have a doubt, you can again think about, when x is greater than 4, is x minus 4 a positive quantity or a negative quantity? If x minus 4 is positive, then absolute value of x minus 4 will be x minus 4. If x minus 4 is a negative quantity, which happens when x is less than 4, then absolute value of x minus 4 will be negative of that quantity. In this case, therefore, your function becomes 1 when x is greater than 4, minus 1 when x is lesser than 4, and at 4, the function has been defined to be 0. So again, the behavior of the function over its entire domain needs to be discussed. So most of you, in fact, would be in a position to comment and say whether this function is a continuous or a discontinuous function. So I think since Tanmay is with me, I'm going to take his help and ask him to give his understanding of what the function is like. Your audio is not clear.
Is it clear now?
There's a lot of background there. If you have a phone, then put it, switch it off or put it a little further away.
Now?
Yeah.
Oh yeah, I was sitting really close to a printer and a computer. I think that's why this happened. Anyway, yeah, so as you showed, you can break this piecewise function from 2 to 3 pieces. And that really is, simplifies it further. I not have expected it otherwise initially. So for x is less than 4, the value of the function is -1, which is nothing but a constant. And a constant is basically a polynomial with the degree 0. So even that is continuous, or if you want to take the limit, then the limit of, say, for some c less than 4, yeah, so in limit of the function as c approaches, no, as x approaches c would be -1. Similarly, for x is greater than 4, value of the function is always 1, so the function is continuous. From that we can deduce that the function is continuous for all points in the domain except 4. However, again, the problem arises that x is equal to 4, where the left-hand limit clearly turns out to be -1 and the right-hand limit turns out to be 1. So these two limits are not equal, hence they do not exist and is not equal to the function at that point. And thus, the function is continuous at all in its domain except x is equal to 4.
So if we think about the what the domain of that function is, and then think about how the graph would look like, since you mentioned something about focusing only on the concept of the degree as a polynomial. So if you don't think about that, but look at the function, then that function becomes very easily recognized to be a function which is two straight lines. There x is equal to 1 and fx is equal to 1 and fx is equal to minus 1, and add x is equal to 4, it takes the value 0. So it's a function that one was very familiar with in grade 11 as well. So if you can recall, it behaves almost like what the signum function did. So we are looking at the graphically also, the function is going to be very, very clearly a discontinuous function. But as an algebraic result, you need to state that in proper language, mathematical language, and that can be done now, as we discussed earlier, taking the help of the results, which Tanmay also had mentioned right now. So when x is greater than 4, fx is equal to 1, which being a constant function is continuous. Now, constant function is continuous is a standard result. Again, I didn't list it out, but if you had heard Tanmay, he said constant function is a polynomial of degree 0. So that's one reason. Constant functions graph can be thought of as a reason behind or as a justification to accept that every constant function is continuous. So constant functions are continuous. It gives us, at least for x greater than 4 and x less than 4, the function to be continuous. Then it's only at x is equal to 4, which again is not really a challenge, because it's very clear that the left hand limit, as one can see here, and the right hand limit, they both are not equal to each other and equal to the value of the function. So it's not at all continuous at x is equal to 4. It's not even left side continuous kind of a function. And therefore the function is continuous everywhere except at x is equal to 4. So that's another way of establishing or discussing the continuity of a given function. So this is a concept which is again depending on evaluation of the limit, but the limit has come with an idea of what the function's behavior is. So if you're looking at algebraic functions, then you're comfortable doing with them. If it's a trigonometric function, then also you were trained well enough last year to handle any of those problems. Now, next is again a solved example from NCERT, and I picked it up because it's something different, and this is quite debatable whether we should do something like this or not. And so I thought it's a good question to take today. It says show that the function f defined by f of x is equal to absolute value of 1 minus x plus absolute x. Now this function needs to be discussed for continuity. So x is any real number, f has entire real number in its domain, and we need to discuss whether it is a continuous function or not. This, if you look deeply, there is lots happening here. You're looking at absolute value of difference and a sum, and again an absolute function coming in. So this is a very complex function, and if you're asked to talk about its continuity, then what NCERT has done, and its very valid solution is to break it down to smaller functions. In this case, they have defined g and h. G to be a function, g of x to be 1 minus x plus mod x, and h as hx is equal to mod x. So when you talk about the given function f, then it's nothing but the composition of h with g in the order HOG. So h of g of x becomes h of 1 minus x plus mod x, and therefore it becomes mod of f of mod of 1 minus x plus mod x, which is f of x. So they say that in an earlier example and otherwise also, modulus absolute functions are all continuous functions. G being sum of a polynomial and modulus function is continuous. But then f being composite of two continuous functions is continuous. So they have taken the help of these little results which I had shown and listed earlier, that sum and difference of continuous functions, polynomial functions, modulus functions, they are continuous, and composition of two continuous functions is also continuous. So this is a way which is quite acceptable. If it becomes a 6-mark question, maybe this method may not be accepted. You may be again required to break it down and think about it over its entire domain. But the results that we have talked about earlier are just the right thing to use to establish that a function which looks quite complex, is made of lots of different functions, is a continuous function. So this is something that I wanted you to think about, and keep in mind that there is a possibility to discuss functions in this way as well. So here's my last question on continuity in this session for you. And as in the last session also, I had asked for you to do one particular problem and post the solution. If you can just take a picture and attach it with your post, that would work. So here's one more question, and here the question is to find values of a and b so that the function f defined as 0 for 0 less than equal to x is lesser than pi by 4 is defined as x plus a root 2 sine x. Between pi by 4 to pi by 2 is defined as 2x cot x plus b, and when x is greater than equal to pi by 2 and lesser than equal to pi is defined as a cos 2x minus b sine x. It looks quite complex, but you can see that the interval, the domain of this function is actually 0 to pi. So over this limited domain, you have to discuss whether the function is, what will be the values of function, what will be the values of a and b so that the function becomes continuous. So you have to make sure that you examine at pi by 4 and at pi by 2. That is where the change is happening, and you have to ensure that the values of a and b are such that the function remains continuous at these 2 points as well as between 0 to pi by 4 to pi by 2, and pi by 2 to pi. So let's see if we have any questions today, or there is no question coming up today. So I think we are good to go. And we'll move on with our another concept, a very big major concept. And I'm very sure that you would find yourself struggling with it many a times as we look ahead into the next few months. So I have to open up another presentation where we are going to talk about the differentiability of a function. So we are looking at a concept of when do we say functions are differentiable. So far we have just given a function, we have just differentiated it without bothering to find out whether the function is actually differentiable or not. That means we just took it for granted that when we are asked to find the derivative would exist and we will end up with an answer. Well, that doesn't actually happen all the time. We are going to face situations where we will understand, and then kind of at the end of it, not today perhaps, we'll also be able to reach a point where we'll be able to understand what exactly is the geometric significance of a function not being differentiable. Like in continuity, if I draw the graph and the graph has a break, we understand that there is going to be a discontinuity. So is there something that we can see using the graphs and comment in terms of the differentiability is also interesting aspect. So we are going to be looking at the concept of differentiability now. So just to recall for you, this was how we have defined derivative of a function at C. So here we are talking about the differentiability of a function at a point, and then it will become the concept over its entire domain. So to begin with, this is how we learned in class 11 to find the derivative of a function at a point. So we found the change in f divided by change in x, and then took the limiting value and called it as an instantaneous rate of change at c, and that was given the notation of f dash c. Every time we talked about this, there was an emphasis on that the derivative of f at c will be defined as and denoted by f dash c to be the limiting value of this quotient if this limit exists. So the whole thing was hinged on this premise that this limit will exist, and we just never came across a situation or never actually explored the possibility that this limit may not exist. So wherever we have found the derivative, we have done it for cases where the limit of this quotient always existed. Now, limit will exist at as x approaches c if the left hand limit of this quantity and the right hand limit exists. And that is what the left hand derivative and right hand derivative are defined as. They are defined to be left hand derivative limit of fx minus f of c upon x minus c as x comes closer and closer to c from its lesser side. So that's how we have talked about left hand limit everywhere, but now it's the left hand limit of this increment ratio, which is change in f divided by change in x, or change in y divided by change in x. Right hand derivative is limit of fx minus f of c by x minus c as x tends to c plus, that is x taking values closer and closer to c but greater than c. And we say that f is differentiable at x is equal to c if these two limits exist and they are equal to each other. So if they are finite and they are equal, then the function is said to be differentiable at x is equal to c. So that is how we are going to be looking at the concept of differentiability of a function at a given point. Now, this leads to the definition of what it means by a function to be differentiable. So a function is said to be differentiable in an interval, closed interval AB in this case, if it is differentiable at every point of that interval. So that is how we are going to be examining or discussing using this idea. Now, this is our very regular problem that you would be dealing with, and once you have mastered one, possibly you can handle any other question of the similar style. So here we are looking at examine the differentiability of the following function at x is equal to 2. Again, 2 becomes a point of interest because at 2 the behavior of the function is changing. So it's x minus 1 linear function, 2x minus 3 also a linear function. So the graph of such a function can always be thought about. You can give it a try and see what kind of an observation you make at 2. I have the graph here for you, and you can see that for x lesser than 2, it's x minus 1, the blue line. Greater than 2, it's 2x minus 3. And at 2, whether you come this way or that way, the height of the function is 1. So there is no gap in the graph. It's very clearly a continuous function graphically when you examine. If you do it algebraically, you will also get the same conclusion. Now our interest is to figure out, is the function differentiable at 2? So I want you to keep this image in your head and see what is happening at x is equal to 2 in terms of the graph. And when we conclude or examine and end up with our result, we will maybe take a look back at this function. So to discuss the differentiability, the definition is that I am following and I would like you to stick to would be to think about right hand derivative to be limit of fx minus f of c by x minus c as x approaches c from its greater side. Write the general definition first and then replace it by the rule that we are following in the problem. So right hand derivative at x is equal to 2 will be limit of fx minus f of 2 upon x minus 2. So c gets replaced by 2 as x tends to 2 from its greater side. Now that becomes a signal for you to replace this f of x. When x is greater than 2, fx was 2x minus 3. F of 2 you can find out either ways. So in this case it turns out to be 1. So your numerator becomes 2x minus 3 minus 1 and the denominator remains x minus 2. That simplifies to be limit of 2 as x tends to 2 from its greater side. That's nothing but 2 again. So right hand derivative is 2. What we have to now find out is the left hand derivative existing, is it finite, and is it equal to 2? So in this case, left hand derivative is limit of f of x minus f of c by x minus c as x tends to c from its lesser side. Our point is 2, so fx minus f of 2 upon x minus 2 as x tends to 2 from its lesser side. When x is less than 2, fx is x minus 1. F of 2 is 1. So the numerator becomes x minus 1 minus 1 upon x minus 2, which is nothing but 1. So limit of 1 as x tends to 2 is also 1. So since left hand derivative is not equal to right hand derivative at x equal to 2, we conclude and say that function is not differentiable at x is equal to 2. So again, if we go back to a graph, then graphically one could say that the function is differentiable, is continuous, and we were examining the differentiability at 2. So now that we have established that the function is not differentiable at x is equal to 2, what I want you to recognize and note that at 2, mathematically and otherwise, we say that there is a corner point. So the graph is not smoothly turning at 2, but there is a sharp corner at x is equal to 2. Any graph which has this sharp corner will not be differentiable at that point where it is getting that corner point. So that is something which we are going to be examining and discussing and referring to even later down the line as we start comparing and thinking about, is there a concept that we need to talk about which would help us to understand if there is a relation between continuity and differentiability. So I want you to hold on to that thought and we'll discuss it further in our next lesson. One last question for today, and the question again is sum of modulus functions, and you have to discuss or show that the function is not differentiable at x is equal to 2. So if you have tried out drawing graphs of such functions in grade 11 and had got some kind of an expertise and comfort level with it, you would know what is happening to this function. Is there going to be a point where there's going to be a sharp corner? Is there going to be more than one such point? And I'll leave that for you to try and get the graph and share with us next time. But right now, as we have done in every problem on modulus, we first rewrite the function. So in this case, when we look at the 2 points that are making this function change its path, take a different definition, that would be at x is equal to 1 and x is equal to 2. So 1 and 2 are the two main points that you need to be careful with. So examine the behavior of the function for x lesser than equal to 1, and then between 1 and 2, and then x greater than equal to 2. And when I say between, well, x is greater than equal to 1 and lesser than equal to 2. So 2 and 1 can be included here with some confidence that the function may be continuous. So that means at x is equal to 1, whether I take a value from here or value from here, they are going to be same. So you can see that they are. Now for x less than equal to 1, again for a few of you who would be maybe watching a recording later, if you are not too confident of how to rewrite these functions, then again think about when x is less than equal to 1, is x minus 1 a positive or a negative quantity? So when x is less than 1, then x minus 1 is a negative quantity. So modulus of x minus 1 will be minus negative of x minus 1. Whereas x minus 2, again, it's a negative quantity. So modulus of x minus 2 will also be negative of x minus 2. So this simplifies and you get something which same as 3 minus 2x. And for x greater than equal to 1, lesser than equal to 2, same technique works, and you would get the function to be taking value 1. For x greater than equal to 2, the function takes the value 2x minus 3. So this becomes our rule that we need to follow when x is less than or greater than 1 and x is greater than or lesser than 2. Once this is done correctly, the rest is again a very mechanical task. Starting with left-hand derivative, and since the problem asks you only to discuss differentiability at 2, our focus is only on 2 right now. So left-hand derivative at x equal to 2 will be limit of fx minus f of 2 by x minus 2. Now this is the main thing. If you know how to write this definition, we are good to go. There is nothing else to do. F of x when x is lesser than 2 followed the rule 1. F of 2 also was 1. So you get 0 by x minus 2, which is limit of 0, which is 0. So left hand derivative is 0. Right hand derivative, again fx minus f of 2 by x minus 2 as x takes values greater than 2 but close to 2. So fx is 2x minus 3 when x is greater than 2. So, and f of 2 is 1. So the numerator becomes 2x minus 4, which is 2 times of x minus 2. Simplifies to limit of 2, which is 2. And then we are almost done. Limit of right hand derivative and the left hand derivative are not equal, and we say therefore the function is not differentiable at x is equal to 2. I think you would have got on to the technique, the method that we are following. So Tanmay, if you have any doubts, you can help me out and let me know if there is something which I have not been able to explain clearly, or you think it would confuse if somebody else. Maybe think about your friends and any of your friends, think of somebody who would have a question, and on their behalf, if you want to ask a particular question, I can clarify your doubt.
No, ma'am, the questions and the concepts are very difficult this time, and even on the Q&A bar, there's nothing there today. So I think you did a job today.
Like either everybody has followed or will follow. Let me take that as a presumption and move on. That if they sit and watch the recording and if they follow the presentation, then all will be well, and I don't need to reteach the entire concept. So I'm not really anxious to teach the whole thing again. In fact, I do have homework, more homework for you today. There are two questions that I want you all to try here now, because this is a 6-mark question that you would get, because it's now double the work. You have to discuss continuity and differentiability of the function at x is equal to 4. So you have both the things to talk about. So this is one question, note it down. Discuss continuity and differentiability of the function f of x is equal to x minus 3 when x is lesser than 4, and 3x minus 11 when x is greater than equal to 4 at x is equal to 4. So that's one question where we have to discuss continuity and differentiability at a point x equal to 4. Another question says, show that the function f defined as follows is continuous at x is equal to 2 but not differentiable thereat. So there is right now, in fact, the question that we did was such that the function was continuous but was failing to be differentiable. So there are many such possible examples, and this is one of them, but now you have to establish this algebraically. You have to show that the function is continuous but not differentiable. So if you have noted down the problem, good. Otherwise, of course, the same would be up on Edmodo and you will be able to note it down. Somewhere as we have progressed today in the lesson, both the concepts and right now in these problems as well, the concept of continuity and differentiability is coming together. So there is a very important, significant result which says that if a function is differentiable at a point C, then f is also continuous at that point. And a corollary of that would be that every differentiable function is continuous. But then the converse of this statement is not true. So this is something that I'm going to take up in our next lesson, because I do want to talk about the proof, an argument to establish what we are looking at. Converse of above is not true is something which I would like you to be ready with. Give an example of a function. We have just done one, but think about something else. A function which is continuous but not differentiable. So we have just seen one example. Another question also is there, but maybe something simpler. You don't have to make a very complex example. Pick a very simple example and be ready with it to say that the converse of above statement, that is, if a function is continuous, it does not imply that it is a differentiable function. Find an example for that and share with us next time, or when we see you on 2nd of July, be ready with an answer for that, because that is going to help us to ensure that we all are on the same plane. So hopefully, Tanmay, you have benefited today by being around and being part of this session, right? So we'll try to squeeze in maybe one more session on Monday and carry on with this discussion, because there are two very important things that I need to finish off before we say that yes, we have at least briefly, if not deeply, covered most of the concepts, right? So if you have any question, you can ask. Otherwise, we'll wind up the session. Right.
Yes, ma'am. This is regarding the presentation, ma'am. I skipped some slides or something because there was one question in which that f is a piecewise function, like if it's f for x is less than equal to 1 and 2ax plus b for x is greater than equal to 1. We have to find a and b if the function is differentiable at x is equal to 1. So
Yeah.
I mean, was that accidental or you intentionally skipped that?
Today?
Yes, ma'am.
I gave that for you to try out, isn't that?
Oh,
Click on differentiate. No,
oh,
no, I've
yeah,
changed
yeah.
the order. I've changed the order of the question. That's for the next time because we do need to know that every differentiable function has to be continuous. All right, so that
Okay.
will be done next time.
All right then.
Right. Thank you. All right, so I think we'll stop the broadcast now, and I do hope that my rest of the gang would find time to look at the recording and come prepared. So Tanmay, do the needful. Maybe you have a better reach to your friends, so spread the word around and ask them to come prepared. Otherwise, face the consequences on 2nd of July. Right? Okay. Bye then. Thank you for joining in.